In this video, we will take another look at percent yield and limiting reactant. We need to remember a few terms from the previous video. One of them is theoretical yield. That's the maximum amount of product that we could produce if everything went perfectly. The actual yield is the amount of product that we find when the reaction actually is carried out, which is always less than your maximum amount. Percent yield is determined by dividing the actual yield by the theoretical yield. You will always get a number less than 100. You multiply that by 100% and you'll get the percent yield. The other terms we need to be aware of are our limiting reagent. That's the reactant that will run out first. It limits the amount of product we're able to make. And then the excess reagent, which is the leftover reactant. When the limiting reagent runs out, one of our reactants will be left over. Now, as it turns out, your first problem on the stochiometry quiz was a limiting reactant problem. I apologize for that. I'm not sure how that got there. I usually do screen the questions a little bit better, but this did appear in a stoichiometry problem, although it actually turns out it wasn't with the unit on limiting reactant where it should have been. But looking at this equation, how many grams of carbon dioxide could be produced from 1.4 grams of carbon monoxide and 1.4 grams of oxygen? So the step one is our balanced equation, which we already have in this particular case. Some of the stoichiometry problems, just to make life a little easier, you will be given a balanced equation and need to make your conclusions from that. Step two, as we've seen before, is to turn your grams into moles. Now, in this particular case, we have 2 gram values. We have the grams of carbon monoxide and we have the grams of oxygen. So it can't hurt to turn them both into moles. Both of these are reactants. You'll notice neither of these is the product. It's asking you for the grams of product we should make, but one of these is going to run out first. Now, just at an initial look, we can see that carbon monoxide, we have more carbon monoxide than oxygen. So it might seem logical to think carbon monoxide will run out first, but we'll have to look a little bit more closely to see what actually runs out. Third step, of course, is to find the mole ratio. This is a very simple one, 1 to 2 to 1, which means for every 2 moles of carbon monoxide, we will need 1 mole of oxygen gas, and we will produce 2 moles of carbon dioxide. Step 3A, which is slightly different, we have to find out which reactant we have an excess of. So we would see which of these products, if it was used to its fullest extent, which of these products would produce the most CO2. In this particular case, oxygen is going to produce 0.088 moles of carbon dioxide, whereas carbon monoxide would only produce 0.050. So we have an excess of oxygen in this case, and we have a limiting reagent, which is carbon monoxide. Once the carbon monoxide runs out, we can't make more than 0.050 moles of CO2. If we had more carbon monoxide, then we could make more CO2 because we have this abundance of oxygen. However, in this particular case, we can't make any more because carbon monoxide is our limiting reagent. Also, just want to point out and really make clear, the mole ratio is for your conversions. Do not confuse this number of moles with the 2 moles to 1 mole, thinking you need to multiply something by 2. No, this is how many moles of carbon monoxide you have. You can't magically make 2 just because that's in the equation, but what you need to do here is use that mole value and use the mole ratio to find out how many moles of carbon dioxide you would make or how many moles of oxygen you would use. So obviously the limiting reagent here is carbon monoxide, and we will put our step 4 calculations where we calculate the products based on the limiting reagent. So we can do the cross multiplication method that I taught earlier, which is 2x equals 2 times 0.050, or we can cross out our units that are given and have the units requested, because really we want to solve for the units of carbon dioxide that we produce. and we would cancel out the moles of carbon monoxide. This is the same canceling of units we've done throughout this year, and I said it's going to just keep coming back in different forms. So we end up producing 0.050 moles of carbon dioxide because the carbon monoxide runs out, and we end up changing the moles to grams with the gram molar mass of carbon dioxide, and we end up with 2.2 grams of carbon dioxide, which was the answer in this particular problem. Now from there, here's a much more apparently challenging problem. It looks much more challenging, but it's the same steps we just did. Don't let the bigger numbers or the uneven numbers intimidate you. Step one is we're going to have to come up with a balanced equation for this particular reaction. Now, this is a little bit of a tricky one because hexane is C6H14, so you know you're going to be making a lot of carbon dioxide and carbon dioxide and water in this particular situation. So there is our balanced equation. We have 38 oxygens. We have 14 plus 24, which is 38 oxygens. We have 28 hydrogens. We have 28 hydrogens. We have 12 carbons. We have 12 carbons. This is a balanced equation. Step 2 is going to be change our gram value that we have, 35.0 grams of hexane. We're changing that into moles. We'll also have to change our oxygen gas, the liters that were given at STP, into moles, which is a different conversion, 31.5 liters times 1 mole over 22.4 liters. Again, you set up your conversions so that you can cancel out the units that you need to get rid of, and you keep the units that you want. So we get 1.4 moles of oxygen. We get 0.41 moles of hexane. Now we have to figure out which one of these is the limiting reagent. We do that by setting up our mole ratio, and then running both of these mole ratios we run them through to determine how much carbon dioxide we would produce, because it says 35.0 grams of carbon dioxide are formed. So we have to put that moles of hexane that we have through our mole ratio conversion. We cancel out our hexanes. We end up with the moles of carbon dioxide produced, which would be 0.41 times 12 divided by 2, which is 2.46 moles of carbon dioxide. In the case of oxygen, we start with 1.40 moles, which is our 31.5 liters at STP changed into a mole value. And then we have the same mole ratio. We cancel out our oxygen. We keep our carbon dioxide. So it would be 1.40 times 12 divided by 19, which is 0.884 moles of carbon dioxide. Initially looking at this, we might think that our hexane is our limiting reactant because it looks like we have fewer moles of it. However, 2 moles of this, you need 19 moles of oxygen, which means in this particular case, oxygen is the limiting reactant. I can't make any more than 0.884 moles of carbon dioxide. There's no way of making more carbon dioxide than that because my oxygen's going to run out. I will have plenty of hexane left over. Step 4, I still have my mole ratio. I will base the production of CO2 on the amount of oxygen that is consumed. If we're assuming all of the oxygen is consumed, that'd be 1.40 moles of oxygen. I run this back through my mole ratio, so I want to get moles of carbon dioxide. I put that on the top because that's my product I'm looking for. I want oxygen moles on the bottom because I want to cancel out my moles of oxygen. So I do 1.4 times 12 divided by 19. The only units I'm left with are moles of carbon dioxide. I end up with 0.884 moles of carbon dioxide. I take that mole value, which is my product of carbon dioxide, I change it back into grams of carbon dioxide, and we see that 35.0 grams of carbon dioxide, which may have seemed kind of ridiculous at the beginning, actually isn't that far off what our product is. And therefore, the percent yield, we would divide our actual yield by the theoretical yield times 100. We get a 90%. Now, I was a little sloppy with the sig figs in this problem, I'll admit, but since I'm basing all of my molar masses on 2 digits, I'm going to give 2 significant digits for my final answer. 90 point, that tells me that both of these digits are significant. 90% is my percent yield. And as we established earlier, the limiting reagent is the oxygen. We don't have enough oxygen to burn all of this hexane. So what would happen, eventually the hexane would just stop burning, we'd run out of oxygen. End of the reaction. And with that, I will let you go ahead and practice some other limiting reactant problems. Thank you.